Let me just recap what we did in the previous session. So the first thing we saw was basics of number systems, right? Basics of number system, and we also saw a bit about its evolution. Of course, we did not go into much detail, but we saw the basic chronology of evolution of number systems. Then we saw complex numbers, how to represent complex numbers, right? X plus iy format. Then we saw their representation in Cartesian form and in polar form, right? So these two forms were very important in the last discussion. Then we went ahead and we saw what is the magnitude of a complex number. So what we saw, magnitude, right? Magnitude, and we saw its argument. So we saw how to find the magnitude, how to find the argument, what is the physical meaning of it, how we represent magnitude and argument in Argand plane, both in Cartesian form and in polar form. Magnitude is also sometimes called modulus, and argument is also, as we saw in the last class itself, that it's called sometimes amplitude, right? Then we went ahead and we saw powers of I. When we raise iota to certain power, then how does it respond? We also saw a very important lemma, a very important concept, that if we add 4 consecutive powers of I, then we always get 0. So this is what we saw, powers of iota. Then we saw, after we saw the argument, we saw what is the principal argument, right? Principal argument. And we saw how to represent it in Argand plane, and then we basically saw some examples. Don't worry, we will solve more examples of whatever we saw in the last class, and I'm just trying to basically finish some fundamentals, some theory of basics of complex number. Then in the later classes, we will certainly see lots and lots of examples which will make things very clear. Now in this class, what we are going to see, I will just give you a recap of what we are going to see, is the very first thing we will see, conjugate of a complex number. Conjugate of complex number. We will see what is the meaning of a conjugate, how do we represent it in Argand plane. Then followed by that, we will see algebraic operation in complex number. What is how do we add two complex number, how do we subtract two complex number, how do we multiply, and how do we divide two complex number. We will see those operations. Then we will see a very basic, rather very important concept in complex number. I think that is the core, that is the crux of the entire complex number, and that is De Moivre's theorem. We will see it after that. De Moivre's theorem. De Moivre's theorem. Okay, this is going to be the most important concept in complex number, and if you understand this, if you understand the application of De Moivre's theorem in a very proper way, then the journey of complex numbers and understanding of it is going to be very, very easy. Then next thing, after we will see De Moivre's theorem, we will uh, try to cover in this um, in this class itself the properties of modulus, followed by properties of argument, and then we will also see properties of conjugates. Okay, and of course at the end of this class we will solve examples. Okay, so let us start with what is the conjugate of a complex number. Okay, conjugate of a complex number. Conjugate of a complex number. So basically, conjugate of a complex number is nothing but its mirror image. Its mirror image with respect to real axis. I will show you how what I mean by that. So let us say I have this argand plane. Okay, this is my real axis. This is my imaginary axis, and this is origin. Right side is positive real axis, negative side is negative real axis. The left side on top of origin is the positive imaginary axis, and downside of origin is negative imaginary axis, right? So what do I mean by conjugate of a complex number is that if I have a complex number, let us say this one. So this is the complex number I have. Okay, let us say I represent it by z is equal to x plus I y. Okay, so what I mean by mirror image of it on real axis is if I put a mirror here, let me put a mirror here. Yeah, let's say this is let us say real axis is the mirror. Okay, if this is the mirror, then if I take mirror image of this point, then I will get this point. No, this point. Mirror image about real axis. Okay, mirror image about the mirror. And if I join this by a complex number here, so this complex number that I get after taking mirror image of z will be called conjugate of z. So this complex number is conjugate of z, and it is represented by z bar, a horizontal line above the z. So can you tell me what will be this complex number? This will be, so this portion is going to remain same. This portion is same for both the complex number. So I will have x, but this portion which was y is now going to become minus y. No, so this complex number will become x minus iy, or rather if I write it like this, x plus I into minus y, which is equal to x minus iy, right? So this complex number, which is the mirror image of z about real axis, is called conjugate of this complex number z. So in a very simple term, if 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 I replace I by minus I in a complex number, then what will I get? Then I will get conjugate of it, conjugate of it, right? So so and conjugate of z is represented as z bar. So if z is equal to x plus iy, then what is z bar? Z bar will become x minus iy. So z bar is nothing but the mirror image of z about real axis. So if you concentrate on this, then you will realize, if I take mirror image of z bar itself, if I take mirror image of z bar about real axis, then what will I get? The conjugate of z bar. That means the conjugate of z bar, that is z bar bar, will become the complex number itself. No, the mirror image of conjugate will go back to the same complex number. So z bar bar will become z. Few more important thing to understand here is that you can see these two arrows, these two vectors, these two vectors are of same length, because this point is, these points are mirror image of each other about real axis. So mod z, modulus of z, is same as modulus of z bar. That means magnitude of a complex number is same as magnitude of its conjugate. And what is important about argument? So what is the argument of z? Will be represented by this. No, let us say this is alpha. So what will be the argument of conjugate, that is z bar? It will be, of course, this angle, but in clockwise direction, right? So if argument of z is alpha, then what is the argument of z bar? What is the argument of z bar? It will be minus alpha. That should be understood. So whenever you think of conjugate, close your eyes, just think of having a mirror image of that complex number with respect to positive, with respect to real axis. So if the complex number is lying below the real axis, mirror image will go above the real axis, and if the complex number is lying above the real axis, its mirror image or the conjugate will go below the real axis. So just few examples, just few examples. If z is equal to 2 plus 3i, then what is z bar? I have told you how to find conjugate of a complex number. In physical sense, you have to get mirror image of it with respect to real axis, and in mathematical term, you have to replace I by minus I, or you have to basically um, reverse the sign of its imaginary component. So the z bar will become 2 minus 3i. That is okay. So can you tell me what is the uh, let me one side, let me write uh, let me write here, let me write z here and z bar here. Okay, and let me write let me write mod of z, let me write mod of z bar. Okay, and let me just create some space, z bar, then I will write mod of z bar. Yeah, okay, so I will write here mod of z, I will write here mod of z bar, I will write here argument of z, and here I will write argument of z bar. So let us say, and here I will write serial number, so 1. If z is 1, so what is z bar? So z is 1, that means imaginary component of this complex number is 0, that means this is a real number lying on the real axis. So the mirror image of this with respect to real axis will be the number itself, right? So z bar will become 1. No, let me draw here uh, something like this. So this is 1. No, this is 1. So the mirror image of this with respect to real axis will be the number itself. So z and z bar will remain same. What is mod of z? Mod of z is 1 because this is 1 unit away. What is mod of z bar? I mean, if both are same, then everything will be same. Argument of z is 0 degree, argument of z bar is 0 degree. Okay, what if z is I? That means z is lying here, right? So what is the mirror image of this point with respect to real axis? It will go here. No, so what will be the z bar? Minus I. I have already told you that if you want to find conjugate of a complex number, just replace I by minus I and you will find the complex numbers conjugate. So that's what I is replaced by minus I. What is the magnitude? That means the distance of this point from the origin. This will remain 1, and here also this will remain 1. So magnitude is same. As I have told you here that magnitude of z is same as magnitude of its conjugate. The important point here is what is the argument of z? This one is pi by 2 radian. No, and what is argument of conjugate? So if this is pi by 2, then this will become minus pi by 2. I am writing in principal argument form. I can write this, it is same as 3 pi by 2. I can write this way, no? So this is nothing but 3 pi by 2. Okay. Number 3, general example. I will take let us say 1 plus I. Okay, so 1 plus I, let me 1 plus I. So what is 1 plus I? 1 plus I is somewhere here. No, so this is 1, this is 1, 1 plus I. So what is the conjugate? Conjugate is mirror image of this with respect to positive with respect to real axis. So of course you can get it by replacing I by minus I. So conjugate is 1 minus I. What is the magnitude of z? Is root 2, same as magnitude of z bar. What is the argument of z? This angle. If you find out this angle, this will be pi by 4, and if you find this angle, this will be minus pi by 4. So we have seen that argument of z, if it is alpha, then argument of z bar is minus alpha. So alpha and minus alpha. So what we have seen here is two things. Two things we can note down. Number one, if z is real, then what? Z is equal to z bar, right? So if a complex number is real, that means if it is lying on the real axis, then its conjugate is same as the number itself. So if we want to prove in some questions, if you want to that prove that this complex number is real, then what you can prove, that that complex number is same as its conjugate, and if that is true, then that complex number is real. We can see here, once we talk about algebraic operations of complex number, then we will see how to add and uh, subtract. But for the time being, you just see if z is real, then z is equal to z bar. And what about, I will let z is purely real, no? And if z is purely imaginary, then z will become z bar with a negative sign. We saw here, no? I is purely imaginary number. I is purely imaginary number. So if I take the conjugate of it, that is minus I, and I multiply it by negative sign, I will get the complex number itself. So take the conjugate, multiply it by negative sign, then you will get the complex number itself if z is purely real. So this is brief about uh, conjugate of a complex number. We will see more about it. Conjugate of a complex number is like, it will solve most difficult problems in a very simple way if you understand few things about complex number, and one of them is conjugate. So conjugates will make things very simple, provided we see some of its properties in subsequent sections and how to apply them while we solve the problems. Now let us see algebraic operation in complex number, and first thing in that we want to algebraic operations in complex numbers. Okay, and what is the first thing we want to see here is addition. Addition. How do we add two complex number, or more than two complex number? It is a very simple operation. You add real part of the complex numbers, you add imaginary part of the complex numbers, and finally get the resultant complex number. An example is like this: if I have z1 is equal to x1 plus iy1, if I have z2 is equal to x2 plus iy2, then z1 plus z2 is defined at is defined as x1 plus x2. So this whole thing will become the real component of the resultant complex number plus I y1 plus y2. Okay, so you add real components all together, you add imaginary components all together, and put it in place of real and imaginary component to find the resultant complex number. In fact, if there are more than two, z1 plus z2 plus z3 plus z4, like that, you add real parts of all the complex number, put it in one bracket. You add imaginary part of all the complex number, put it in one bracket, multiplied by I, and get the resultant complex number. And the subtraction, addition, and I will say subtraction, no, subtraction, and you subtract also in the same way. Z1 minus Z2 is equal to, I will write x1 plus Iy1 minus x2 plus Iy2. So if you see in algebra, subtraction is nothing but addition only, but with the sign reversed. So we should not treat subtraction differently than the addition. So this becomes x1 minus x2 plus I, and you can take this y1 minus y2. So this becomes the real part and this becomes the imaginary part. Okay. Second thing, second what is second thing? Multiplication. You can see multiplication. So if there are two complex numbers and you want to multiply them, you just basically distribute the multiplication in the bracket, and I'll tell you how. So z1 into z2. So z1 is x1 plus iy1, z2 is x2 plus iy2. What is z1 into z2? Is like this, x1 plus, I'm not spending much time here in algebra of complex number, because um, of course when you practice more you can easily figure out how to add, how to multiply, and how to divide. I will basically go further into de Moivre's theorem, properties of modulus, argument and conjugate, and spend more time there so that you understand the concepts in a very crisp way. Here I am just rushing it off. Okay. Into x2 plus I by 2. So I will just take this and distribute over this bracket. So x2 is multiplied to x1. So this becomes x1 x2 plus this x2 is multiplied. Let me put multiplication sign here. No. So multiplied here. This becomes I x2 y1 plus this term now gets multiplied to x1, becomes I x1 y2, and plus this becomes I square y1 y2. Okay. So if you write it like this, x1 x2 plus, I can take I common here, this will become x1 y2 plus x2 y1, and I square becomes minus 1, so this becomes minus y1 y2. So I will collect all the real terms. This will be x1 x2 minus y1 y2 plus I x1 y2 plus x2 y1. So this becomes the multiplication of two complex numbers z1 and z2. Is simple, right? So let me just quickly take one example. If I want to multiply 1 plus I to 2 plus 3i, what will I get? I'll multiply 2 by this first, so I'll get 2 plus 2i, then I'll multiply 3i to 1 and I, so 3i into 1 is plus 3i, and this becomes 3i square. So this becomes 2 plus I, 2 plus 3, or rather 2i plus 3i is 5i. Why am I doing kids job here? So 2i plus 3i is 5i, and this is minus I square is minus 1, this becomes minus 3. So ultimately it becomes minus 1 plus 5i, right? So addition of two complex number is a complex number. If you subtract one complex number from another complex number, you get a complex number. If you multiply two complex number, then also you get a complex number. Okay. Basically this is, if you study set theory, then this is called the closure problem. So complex number basically follow the closure law. Okay. So the addition, subtraction, division, multiplication lie in the set itself. That is called the closure law. Maybe when we discuss about set theory in detail, we will take this concept of closure law and distributive and additive law and all that. Third, let us see, third one is division. Okay, how do we divide two complex number? Okay, so to divide one complex number from other, here is the first use of conjugate. This is where the first time we will use the conjugate of complex number, and we will see how it will help us. Before that, let me tell you, if I multiply a complex number with its conjugate, if I multiply a complex number with its conjugate, you know what I get? I get the modulus of that complex number square. I will prove it. So x plus iy, if I multiply it by x minus iy, that is the conjugate. No, this is the z complex number. This is the conjugate of z. So if you do this, you get x square, no, plus I xy, no, this is what, minus I xy, and this is what, minus I square y square, and I square is minus 1, so this becomes plus y square. So this is x square plus y square, and this is nothing but complex number, mod of complex number is square, because what if z is equal to x plus iy, we have seen, then mod of z is under root of x square plus y square. We have seen in the previous class, no? So mod z square will become x square plus y square. So this is one important lemma or concept you can remember. It is used very frequently. Z bar is equal to mod z square. Multiply complex number by its conjugate, you will get the square of magnitude of that complex number. This property is going to be used in division. So the main thing that comes out from here is, if you have a complex number z, you have a complex number z bar. So basically left hand side you have two complex number, but the right hand side you have a real number. So if you want to make a complex number real, then you multiply that complex number by its conjugate, and the resultant will be the real number. So that is the property that we will use. So I am coming back to division. Z1 is equal to x1 plus iy1, and z2 is equal to x2 plus iy2, and I want to find out what is z1 by z2. This is what is the goal of this exercise, no, to find out the division. So I will do it here. X1 plus iy1 divided by x2 plus iy2. Now just remember this. This is the you have to remember this concept as long as you are into the complex number, that whenever you get a complex number in the denominator, of course you have to put the condition that x2 and y2 are not simultaneously equal to 0, otherwise denominator will be 0 and that division will not be defined. So whenever you get a complex number in the denominator, the very first thing you have to do is make the denominator real. And how do you make the denominator real? By multiplying this complex number by its conjugate. So this is the second step. You have x1 plus iy1 divided by x2 plus iy2, and you are going to multiply by conjugate of the denominator, x2 minus iy2. Since you have multiplied here, so you have to multiply here also. No. So now this is z bar. The denominator will become mod z square, right? What is mod z square? X2 square plus y2 square, that we have seen here. We have seen here. So this will become, let me multiply the numerators, x1 x2 plus I will write now directly, okay. This is x2 y1 minus x1 y2, and this one will become minus, this will become plus y1 y2, and in the numerator we will get, if you multiply this, you will come here only. So that is the z bar is equal to mod z square, which is equal to x square plus y square. So now if I separate out, I will write x1 x2 plus y1 y2 in the numerator, and I will separate out, divide by x2 square plus y2 square plus I, and this is x2 y1 minus x1 y2 divide by x2 square plus y2 square. This becomes z1 by z2. So this becomes this thing. This thing is basically what? The real component of this complex number, and this thing will become the imaginary component of this complex number. No, I will write I here. Okay, so this becomes the, sorry, okay, so this becomes the real component of z1 by z2, and this becomes the imaginary component of z1 by z2. I am purposefully doing these small steps here for you to appreciate what we are going to do in the subsequent classes. These longer steps are not necessary or may not be necessary in subsequent classes if you understand the concepts of properties of modulus, properties of argument, properties of conjugate, and we will use it in subsequent classes. But I want you to understand, I want to show you that if we continue doing these long steps, then probably we might take little more time to solve the same problem, which we can solve in another way, which we will discuss later. But right now, basics are the first thing that we have to understand. Okay, so we have seen addition, subtraction, uh, multiplication, and division of complex numbers. So let us say z1 and z2 are two complex numbers. Then, so they are two complex numbers. Then we say z1 plus z2, that is addition of these two complex numbers or subtraction of these two complex numbers, z1 into z2 and z1 by z2, they will all belong to complex numbers. So if z1 and z2 are complex number, then their addition, their multiplication, and their division will also lie into the set of complex numbers. That is exactly the closure law. So addition, subtraction, and multiplication, division also follow the closure law, right? So this is one thing that I want to emphasize here. Second thing, we have already seen that inequalities have no meaning in complex numbers, right? But there is a meaning of equality in complex number. So I say if z1 equal to z2, this statement this statement z1 is equal to z2 means that if z1 is equal to z2, then real of z1 will be equal to real of z2, and imaginary of z1 will be equal to imaginary part of z2. And this is what is the meaning of equality of complex numbers. So let us say I have z1 is equal to x1 plus iy1, z2 is equal to x2 plus iy2. Then if z1 is equal to z2, this implies x1 is equal to x2, and simultaneously y1 equal to y2. These two equalities should hold true if two complex numbers are equal. So that is the meaning of equality of complex number. So that also we have seen, right? Okay. Now just one thing I want to emphasize here, that the number 0, you can consider that as purely real number or purely imaginary number. So that is the only number which falls into both the categories. Other numbers are either purely real or purely complex, or rather purely imaginary. And if the number is not purely real or purely imaginary, then it is a complex number. Okay, so neither real part is 0 nor imaginary part is 0. That will make the number complex, right? Now we will see the most important concept in complex number, and that is the De Moivre's theorem. So we are going to see now De Moivre's theorem. So De Moivre's theorem is of course usually uh, applied to the polar form of complex number, but there is no restriction on that. We can apply De Moivre's theorem in any form of complex numbers, and we will see how. But this is very important, just concentrate on this. We will not go to the proof of this De Moivre's theorem, rather I'll tell you what is this, and then we will move to the application of De Moivre's theorem. How do we apply De Moivre's theorem in solving problems in complex number? So De Moivre's theorem is basically like this: if n is any integer, so I say n belongs to, I can say integer, then cos theta plus I sin theta raised to the power n will become equal to cos n theta plus I sin n theta. This is precisely the De Moivre's theorem. This is very important, and when, believe me, when I start telling the application of this, or rather how to apply this in solving the problems in complex numbers, things are going to be very easy. So this is the De Moivre's theorem. Okay. We can also write, since cos theta plus I sin theta is written as cis theta, so I can very well write cis theta to the power n is equal to cis and theta. So this is somewhat little easier to remember, no? Okay. So this was the first version of De Moivre's theorem. Second, so I will call it first version. Second is, if n is a rational number, rational number. So let us say n is equal to p by q. N is equal to p by q. So when I raise cis theta, I will not write now cos theta plus I sin theta. I'll just write cis theta. So when I raise cis theta to the power n, since n is a rational number, it is nothing but is equal to p by q. So the value of this cis theta to the power n will not be a single value. Will not be a single value. Basically, cis theta to the power n will have q values. Will have q values. We will sometimes see this why this is so, but for the moment you just see this, that cis theta to the power n, one value of this will be equal to cis n theta. It is same as we have seen in case when n is integer, it is same, but since in case of integer this is the only value, and when n is not the integer, this is one of the value. So there will be other values also. Out of that, cis and theta will also be one of the value. Okay, so this also I'll put it in bracket. I'll put it in box, sorry. So this is the De Moivre's theorem. So you have to remember this: cis theta to the power n is equal to cis n theta. Very simple. If n is an integer, if n is an integer, then this is the only value. If n is not an integer, if n is a rational number, then this is one of the value. So that is what we are going to remember. Now after seeing this, now I will move to properties of modulus, properties of argument, and properties of conjugate. Okay, so first thing I will take here is properties of modulus. Properties of modulus, and I have basically stated De Moivre's theorem before telling you properties of modulus, because I am going to use that De Moivre's theorem in now most of the places, and you will realize it is very easy. So let us see properties of modulus. The first property is that modulus of multiplication of several complex number, if I multiply n complex numbers and take their mod, this is equal to the multiplication of individual modulus of complex numbers. This is equal to z1, z2, z3 multiplied by zn. So this is the first property. See, if I have 5 complex numbers and if I multiply them, then the modulus of that multiplication will be equal to multiplication of respective modulus of complex numbers. I can take this to prove it, but I will not take for n complex number. I will take for um, 2 complex numbers. So z1, z2, I will prove this to be equal to mod z1 mod z2. This I will prove, right? So I will start with taking Z1 is equal to, let us say, R1 cis theta 1, and I will take Z2 as R2 cis theta 2. So what is the magnitude of Z1? That is nothing but R1. What is the argument of Z1? That is nothing but theta 1. That is precisely the form, polar form, where theta and R are written in place of magnitude and the argument. Similarly, what is the magnitude of Z2? That is R2. And what is the argument of Z2? Is theta 2. So if I multiply Z1, Z2, let us say I'll take LHS. LHS is Z1, Z2, that is R1 cos theta 1 plus I sin theta 1, no, into R2 and cos theta 2 plus I sin theta 2 mod, no. So this will be equal to R1 R2 R1 R2, and this if I multiply I will get cos theta 1 cos theta 2, right? And you can multiply and check. This becomes I sin theta 1 cos theta 2, and this becomes cos theta 1 I sin theta 2. So this is this, plus I will get I sin theta 1 cos theta 2 plus sin theta 2 cos theta 1, right? I have taken I common out, and this becomes I square sin theta 1 sin theta 2, that is nothing but minus I square is minus 1, so minus sin theta 1 sin theta 2, no. So this becomes R1 R2 and I'll take here as real component cos theta 1 cos theta 2, this one, minus sin theta 1 sin theta 2, right? And plus I sin theta 1 cos theta 2 plus cos theta 1 sin theta 2 becomes sin theta 1 plus theta 2, no, mod. So this becomes mod R1 R2 cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 becomes cos theta 1 plus theta 2 plus I sin this part, no, theta 1 plus theta 2 mod, and this becomes mod R1 R2. This becomes, so what is this? This is like cos alpha plus I sin alpha, where in place of alpha I have written theta 1 plus theta 2. So I can write cis theta 1 plus theta 2. So now this becomes form of R cis theta. So this is R cis theta, R cis theta. This is the form of R cis theta. And what is the magnitude of R cis theta? Is R. That is precisely the polar form, right? So R cis theta, so this is in place of magnitude and this is in place of argument. That means the magnitude of this is R1 R2, because we have put mod sign here, no. So magnitude becomes R1 R2, and that is nothing but, what is R1? R1 is magnitude of Z1, and what is R2? Magnitude of Z2. So what we have proven here? We have proven that the magnitude of multiplication of two complex numbers Z1 Z2 is equal to multiplication of their respective magnitudes. So that is the first property. That is the first property. I will not take the proof for other properties, but I'll just tell you those properties and we'll utilize them when we solve the problems or examples. Okay. So by that property number 1, if I extend this, then I get another property, z to the power n becomes, the mod of z to the power n becomes mod of z to the power n, like this. This is clear, right? Because I can distribute this into z into z into z into z n times, and this is nothing but multiplication of the respective mod z, mod z, mod z, mod z n times the first property, right? This is where the first property has been applied, and this is nothing but mod z to the power n. That's what precisely it is written, no? So this is the second property. What is third property? Third property is also very useful, z1 by z2. If I divide two complex number and take the magnitude of them, that becomes mod z1 by mod z2. You have to remember few properties, not all, but at least some properties you have to remember, and that we will see how easy it will become to solve the examples. It is obvious from here the denominator, that is z2, should not be equal to 0. z2 cannot be equal to 0. Okay. What is the fourth property we will see? It's very important. Z bar. We have seen in um, previous, I think previous session or maybe a few minutes before, that Z bar is nothing but mod Z square. This is also one property that is very important. And last property for modulus I will tell here is, we have seen in case of conjugate that modulus of conjugate and the modulus of the complex number is same, right? So I can write magnitude of z is same as magnitude of its conjugate. That is also very important property we have to remember. So this was about properties of modulus. Next I will take properties of uh, argument. So I will take properties of argument. Properties of argument. Okay. So what is the first property we are going to see here is, first property is argument of multiplication of several complex numbers is nothing but multiplication, or rather sorry, uh, if I multiply n complex number and take the argument, then this will be equal to addition of their respective arguments. So this will be equal to argument z1 plus argument z2 and so on plus argument zn. So in case of two complex numbers, it becomes argument of z1 z2 is equal to argument of z1 plus argument of z2. I will not take proof of this, I will just state this here. You can refer any standard textbook of 11th or 12th standard, and you will find the proof of this. This is a very simple property. Second one is, so if I extend it the way I extended the first property of modulus, then argument of z to the power n will become, so basically then I will add argument of z n times, so this becomes n argument of z, right? Third property, argument of z1 by z2 is equal to argument of z1 minus argument of Z2. So this is another important property that we will use, and I think for the time being we will see only three properties of argument, and that will be sufficient for us to solve most of the complex number problems in 11th and 12th standard and in competitions like JEE and other engineering entrance exams. So these three properties of argument and these five properties of modulus. First property is about multiplication, second property is same, third property is division for modulus, z bar is equal to mod z square, and mod z is equal to the magnitude of its conjugate. Okay, next thing we will see properties of conjugate. Properties of conjugates. And the first property that we will see is, or I will write here, is conjugate of multiplication of various complex numbers. So if I multiply n complex number and take the conjugate of them, then I will get multiplication of their respective conjugate. This is the property, very useful, and it will be very frequently used to solve the problems. Second, in line, the way we saw properties of modulus and argument is z to the power n. If I multiply z n times and take the conjugate, right, then what will I get? Basically, I will multiply conjugate of z n times like this, right? So this will become, okay, you can just do little mathematics and expand it and apply the first property, you will get this. Okay, third one about division, z1 upon z2, if I divide this and take the conjugate, then is equal to z1 upon z2. So I can say this bar basically distributes to respective complex numbers, then this bar or this conjugate also distributes to division, and of course every time I write division I have to be careful that the denominator is not equal to 0. Then fourth property, we have seen this in properties of magnitude, but since it is related to conjugate I will write it here again. Mod z square is equal to zz bar. Next one, 5, I can see z1 plus z2 plus, let us say, zn. So if I add n complex number and take the conjugate, then this will be equal to summation of respective conjugates. Okay, so this is also very important property, very frequently used in solving the complex number problems. And in line with this, z1 minus z2 bar will be equal to z1 bar minus z2 bar. So as I have told previously that subtraction is nothing but addition with reverse sign. Okay, this property that I am going to write now is also very important, that if I add a complex number to its conjugate, if I add complex number to its conjugate, you get a purely real number. What you get is a purely real number. We can check if z is x plus iy, and if I add this to its conjugate, that is x minus iy, what will I get? I will get 2x. So z plus z bar is purely real and equal to 2 real component of z, right? Similarly, z minus z bar is purely imaginary, we can check x plus iy minus x minus iy, no, so x is getting cancelled and what you get is 2iy. So z minus z bar is a purely imaginary number, okay, and this I can write is equal to 2i imaginary of z, 2iy, right? And the last one I will see here is, if I take conjugate of conjugate, then I will get the complex number back, right? We have seen it in um, when we saw conjugates in argon plane. So when you take the reflection of reflection about real axis, you reach to the same complex number, okay. So these properties we just have to keep in mind, and now you will see when we start solving the problems, things are going to be very easy, okay.